So we'll talk today about the birth and the death of stars. And it is something that you may never have thought about, but yeah, there is a beginning to you and to me, and an end, and the same is true for stars. We do not understand very well the details of the birth of stars. It's rather complicated, a lot of mysteries about it. We know more, much more about the lives of stars and about their death, although even there are big gaps, big parts which we do not understand very well. But we know they exist. That's non-negotiable. And we also know that the energy of the stars is nuclear energy. So for those of you who are in favor of solar energy over nuclear energy, don't make the mistake. Solar energy is nuclear energy. The sun burns on a nuclear furnace, hydrogen burning, and that is no different from a hydrogen bomb. The sun and all other stars are nuclear furnaces. So I first want to convince you, first of all I have to learn how this all works, convince you that stars exist. So let's look at some areas in our own galaxy where we think that stars are being formed. And it gives me a chance then to get used to all this fancy stuff here. So if I can have the first slide. Yeah, that is fine, that is great. So this is, where is that? Oh boy. Boy, that's special. So this is an area in our own galaxy. Our galaxy has about 100 billion stars. Sun is only one of them. And this is an area where stars are born. This is an enormous cloud which has several million times the amount of mass that we have in the sun. And under its own gravitational pull, it falls in on itself. We can call that gravitational collapse, nice word. And then you will get nuggets of stars which are formed in this cloud. And that effectively means that as the matter falls in, it gets higher and higher speed, and then speed in a way is heat. When you drop something on the floor, then it has speed, that means energy, but when it comes to a halt on the floor, it converts that energy of motion into heat. And the heat is so enormous when this cloud collapses onto itself that you get temperatures tens of millions of degrees, and that's when the nuclear furnace starts. It ignites, so there are moments that the star is born when it actually ignites. And then we see the next slide. So this is a wonderful slide made with the Hubble Space Telescope. Made it to the front page of the New York Times. Gaseous pillars in M16. M16 is an area in our own galaxy. And what is so interesting, which is typical for NASA to have a little bit of public relations, they call them pillars. And a pillar is something that stands up. If you look at the next slide, now they are not pillars anymore. So NASA would never show you the slide this way, but it's the same area in the sky. And this is also an area where undoubtedly new stars are born. So this is also a gas cloud which is collapsing onto itself. And there's dust also, and you're looking through some of the dust. And so you see here also an area where stars are born. The next slide, please. This is a galaxy somewhat similar to our own. And the galaxy has about 100 billion stars. And there are some smaller galaxies which are satellite galaxies. We also have two satellite galaxies, but you cannot see them from the United States. You must go further south. But they're beautiful. They're really gorgeous in the sky. They're called the Magellanic Clouds, two of them. This galaxy called the Andromeda Nebula also has two satellite galaxies. And so all this light that you see here is merged light of tens of billions of stars. Because if you think that these stars are part of the nebula, that's not true. These are stars in our own galaxy. You have to look through our own galaxy in order to see a galaxy outside our own. So these stars are in our galaxy, and then this whole pancake is the Andromeda Nebula. This is at a distance from us of about 2 million light years. That means light takes 2 million years to travel from this object to us. So the picture that you see is really the situation as it was 2 million years ago. With astronomy, we always look back in time, which is a great thing. And the further back in time you look, the farther objects are away from you. And it is very hard to give you a feeling for the distance of a light year. It's unimaginable, not only for you, but it's also unimaginable for me and for Professor Vazio. It is a light year. Yeah, you can say to a student, okay, that's the distance that light travels in 1 year. But that's so unimaginable. If you were to travel that distance with an airplane, and an airplane, say, goes something like 500 miles per hour, then it would take you 1 million years with an airplane to travel that distance of 1 light year. So it is unimaginable. So don't even try to imagine. That's just the wrong thing to do. Just think about it that it took light 2 million years to travel from this galaxy to us, and that you see here a collection of about 100 billion stars, and you cannot see the individual stars. It's all merged. The next slide shows you another galaxy. It's a beautiful one. Maybe you can focus a little better. And you see this one, you see a spiral structure, has spiral arms, just like our own galaxy. And you can see these spiral arms very nicely, and that's actually where the young stars are born. These stars are typically not older maybe than 10, 20 million years. And the ones here in the middle can be much older, like our own sun, which is about 5 billion years old. But in these arms, we have birth of young stars. So that's enough for now. If we can go back to normal conditions, I think that goes this way. And we raise this. So as I mentioned, stars begin their life by burning nuclear fuel, which is hydrogen. And that's what our sun is doing now. And then later on, they change the nuclear burning of hydrogen to helium. Helium is also formed in the process of the nuclear furnace, but is also present there to start with. And when it makes this conversion in burning its hydrogen to helium, then it swells up enormously. There is more energy that is produced in that second phase, and when there is more energy, there is more heat. And so you can easily imagine that if you have here a star, and so there is this heat source, this furnace inside, which pushes it out, that's the pressure of the hot gas, wants to make it large, but on the other hand, there is gravity that wants to pull it in, so gravity holds it together, and then there is some kind of equilibrium. But the moment that you make the furnace stronger, the star will swell up. And we give that phase a name. We call those stars that are in that phase, we call them red giants. They're huge. They're about 50 times larger than our sun is. And our sun is going to do that. There comes a time that our sun will be 50 times larger in the sky than it is now. You're not going to live to see that. It will take about 5 billion years for that to happen. And then the sun will become so big in the sky that it will be about 30 degrees in the sky, which is this big. Imagine a sunrise like that, and then a sunset of a star this big. But the Earth will not survive that. The Earth will probably melt, and all the inner planets will go away. But that's the fate of our star, of our sun. And then what happens in that late phase, when the star is enormous, the outer layers, we call that the atmosphere of the stars, in general are driven off. They are expelled. And what is left over is the nuclear furnace, which is the core of the nuclear waste. And that core is what we call a white dwarf. Strange name, but that's what we call it. And that white dwarf, that core, is about 100 times smaller than the sun itself. It's about the size of the Earth. It's not much larger. But the amount of matter in that core is enormous. Could be easily half the total mass of the sun. So now you have to imagine that, say, roughly half the mass of the sun is all in that core, which has about the size of the Earth. So that means that the density of that material is enormous. It's about 1,000,000 times higher than the density of water. If you take 1 gallon of water, that weighs about 8 pounds. Now you all know that. When you go to the supermarket, you buy a gallon of something, it weighs about 8 pounds. Whether it's milk or whether it is beer, doesn't matter. It's about the same. It's about 8 pounds. But now, if that were a gallon of material from a white dwarf, then it would weigh 8,000,000 pounds, 1,000,000 times more, because of this incredibly high density. A white dwarf in the sky is faint. The reason why it is faint is because it is so small. I'm not going to throw too many equations at you, but a few, I have no choice. Well, I have a choice, but I chose not to. So you're going to see a few equations. The amount of light that you see per second, we have a name for that, luminosity. It's the power that radiates away. It's immediately obvious that that power is proportional to the surface area of the star. If the star is larger, you get more light. And since you know or should know that the surface area of a sphere is proportional with the radius square, it means that if a star is twice as large, the surface area is 4 times larger, so you get 4 times more light. And so the amount of energy that comes from a star is proportional to the radius of the star, this is the radius, squared. And some of you may even be so advanced that you know that the surface area of a sphere is 4 pi r squared. The 4 pi is a bit difficult for some. But in any case, it's proportional to r squared. And then, which is not so intuitive, the amount of energy that comes out per second is also depends on the temperature of the star. The hotter the star, the more energy. That is perhaps intuitive. What is not so intuitive, that it is proportional to the 4th power of the temperature. And this temperature is not in degrees Fahrenheit. Degrees Fahrenheit is an uncivilized unit. We never use degrees Fahrenheit in physics. We use something else. And if you're interested what that something else is, we can talk about that later. But it is a temperature scale, which is called the Kelvin scale, which some of you may know about. And it is that temperature that we need. We take that to the power 4. And so when the temperature from one star compared with another is twice as high, with the same radius, you have 16 times more light. Okay, so that sets the tone now for the white dwarf. So the white dwarf is extremely small. The temperature, of course, that is a different issue. If you compare our sun with a white dwarf, and if you assume that the temperature were the same, if you make that assumption, that the sun has the same temperature as a white dwarf, then, since the white dwarf is 100 times smaller, the amount of light that it emits is 10,000 times less. Can we agree? Because 100 square is 10,000. So you have 10,000 times less light, so that's why it's very difficult to see white dwarfs. They are not very bright. In 1836, based on observational data, the mathematician Bessel, very famous mathematician, predicted a dark companion of the brightest star in the sky, which is called Sirius. And he predicted that Sirius would have a mass roughly the same as our sun, and that this dark companion, which we cannot see, also about the same amount of mass of our sun. And he mentioned that these two stars, one invisible and the other visible, go around each other, called a binary system, and that this period of going around each other would be 50 years. Well, a binary system with an orbital period of 50 years. And Bessel wrote a very famous letter to Alexander von Humboldt, and I will translate a paragraph from that very famous letter. So Bessel wrote to von Humboldt, "I adhere to the conviction that the star Sirius is a binary system consisting of a visible and an invisible star. There is no reason to suppose that luminosity is an essential quality of cosmic bodies. Visibilities of countless stars is no argument against the invisibility of countless others. Think about that. What an incredible wisdom. It is a statement of profound depth. I will read it again. Visibilities of countless stars is no argument against the invisibility of countless others. So it is scientifically a very important statement, and it also has, of course, great philosophical value, because what we can't see, we don't believe. So Bessel started what we now call the astronomy of the invisible. And it was in 1862, which was 25 years later, when Alvan Clark and his son built a new telescope in Cambridge, Massachusetts, where I happen to live. They built a new telescope, and they were testing that telescope. And they were testing it when Sirius was rising above the skyline of Boston. May not have been a very interesting skyline in 1862. But in any case, they pointed their telescope at Sirius, and they immediately discovered the companion, the invisible companion. So that telescope was powerful enough to see Sirius A, which is the bright star, and the other companion, the faint one, is now called Sirius B. And Sirius B is about 10,000 times fainter than Sirius A. Remember, we reasoned that way, that if the area, if the radius is 100 times smaller, then you would expect 10,000 times less light. Now, even though it was known at the time, very roughly, that a large star would radiate a lot of light, and it was also known that the higher the temperature, the more light, this relation, as you see it here, was not known in that form. But it was realized that if you have so little light, as you see from Sirius B, that there are only two choices. Either the star is indeed very small and has the same temperature, say, as our sun, or it may have the same size as our sun, but then the temperature has to be much smaller. And you are now almost experts. I've converted you into experts. If you assume that the temperature is the same as the sun, then you have to make the radius 100 times smaller than the sun, because you see 10,000 times less light. If you assume that the radius is the same as the sun, then you have to make the temperature 10 times lower, because 10 to the power 4 is 10,000. So you have a choice. And so at the time, it was left open which of the two is true. The idea that the star would be 100 times smaller in size was considered absurd. And the reason why that was considered absurd is that that would give this star such a high density. I just mentioned that 1 gallon of that material would then weigh 8 million pounds, and that was considered absurd. And so there were articles even written about this possible absurdity, that this couldn't be a star that was very small. So it was generally accepted that it was just a cold star. So the idea that it was small and hot was early on rejected. Now in 1910, it became possible to determine the temperature of a star. And that was done through spectroscopic means. If you look at the sun, and you look through it as a spectrum, you can do that with a prism, or you can do that in other ways. You can see all the colors. If you see the rainbow, you see all the colors from the sun. And the various combinations of blue light, and yellow light, and green light, and red light are unique for the color. So when an astronomer sees what he calls this spectrum, so the various components of the colors, he can tell the temperature of that star. And it was in 1914 that this technique was used on Sirius B by Walter Adams. And he concluded that the temperature was even larger than that of our sun. For those of you who understand the Kelvin scale, he decided that Sirius B was 8,000 degrees Kelvin. Our sun is only about 6,000 degrees, so it's higher than the sun. We now know that 8,000 wasn't quite correct. It's really more like 30,000, but in any case, we can agree that the white dwarf, that star, was very hot. And once you accept the fact that it is very hot, you have no choice, but you must make the radius very small. Otherwise, you cannot explain why there is so little light. And so now you must accept the idea that the density is so absurdly high that 1 gallon of that material would weigh 8 million pounds. And Sir Arthur Eddington, a very famous astronomer, he wrote in popular books in the 20s, and he really made fun of this idea. The whole idea of this white dwarf was a laughing stock, even among professionals. They were not willing to accept the fact that there was such high density in our universe that a gallon would weigh something like 8 million pounds. But, of course, science goes on, and it was demonstrated shortly afterwards that the interpretation of the small radius is correct. And the way that that was done is rather sophisticated and a little difficult for you to follow, certainly for the 3-year-old that I saw walking in. Where's the 3-year-old? I saw a 3-year-old walking in. It's no longer there. Oh, you're there? No, you're not 3 years. So this came out of Einstein's theory of general relativity, which was proposed in 1915. And with Einstein's theory of general relativity, he argued that if light leaves an object, that there is a shift in color. And if that object has a very high mass but a very low radius, the shift in color is very strong. And we have a name for that. In astronomy, we call that redshift. The reason why we call it redshift is that the colors that come from the star are shifted. When you look at it from the Earth, they are shifted a little bit in the direction of the red light. So the green light becomes a little redder and the blue light becomes a little greener. That's why we call it redshift. And this redshift was measured from Sirius B, and it confirmed indeed, beyond the shadow of a doubt, this very small radius. And so that's the discovery then of the first white dwarf. The white dwarf, in a way, is the death of a star. It's what the sun will do ultimately. After it dies, it becomes a white dwarf, and then it becomes very faint. So now I want to leave the white dwarfs alone, and I want to go to what Professor Rassio meant.